So in this small lecture series, we are going to introduce the frequency response analysis and Bode plots. And in that context, I'm going to start from the very beginning. And in this one, I'm going to define the concept of frequency response, and we are going to derive a certain important property that if you are already familiar with this topic, you might already know that while doing the frequency response analysis, we often replace S with j omega in the transfer functions. And I believe you understand transfer functions. Otherwise, please go back to the previous lectures. So while doing the frequency response analysis, we often replace S with j omega, right? So we're going to explain that and prove in a mathematical way why that is so, right? And we should also define the concept of frequency response itself, all right? But let's start by figuring out what the response of a system really is, right? So imagine I have, again, as the other lectures went, we are going to consider the system to be linear and time invariant. Also, we are going to consider the system to be in continuous time. So it's a continuous time, linear time invariant system. And for my convenience, I'm assuming a single input, single output system, so that we just have a single transfer function defining the system. All right. In any case, if I have a system, okay, and if I excite that system with a unit impulse signal, whatever output that system produces is known as the impulse response of the system. So here GT is the impulse response of the system, right? Now, so impulse response, and we have already previously kind of derived in a way, derived that impulse response is for a LTI system, for a linear time invariant system, is pretty much describes everything about the system, more or less, right? In fact, so we often define a system, an LTI system, in terms of its impulse response. So if I know the impulse response of an LTI system, we actually know everything about the system, right? Now, if the impulse response of an LTI system is GT, and if I excite that system with any arbitrary input xt, then, and if for that input the output is yt, then it can be shown that for this system, for this CISO LTI system, for this CT LTI system, so we are defining, again, we are assuming continuous time, linear time invariant systems, right? For this continuous time, linear time invariant system, the output yt, this signal yt, is a convolution sum or convolution integral in this case of the input signal and the impulse response. So if I take the input signal and take a convolution and convolve it with the impulse response, we get the output. This is again one of the fundamental properties of linear time invariant systems. This happens for this kind of systems, right? So that's not a difficult thing to understand, I believe, right? So again, this convolution operation is commutative in nature, so it does not matter whether GT appears first or XT appears first. And this also has a very what should I say, very interesting implication, if the impulse response is XT instead and the input is GT, the same output is produced, right? So kind of signals and systems are analogous in a sense, right? So instead of writing XT convolving with GT, we can write this as GT convolved with XT as well, okay? That's again very simple convolution, right? So now let's write down the definition of this convolution operation. So this convolution is again defined with this integral. Again, in our earlier lectures on signals and systems, we actually derived all these expressions, and why this convolution actually gives you the output can be entirely derived by the definition of linearity and time invariance actually, right? So let's write g tau x t minus tau and d tau. So this integral actually gives you this convolution, okay? That's fine, I think, right? So now imagine we have this system, and now instead of exciting this system with any arbitrary input signal, we are exciting this system with a very special input signal, and that very special input signal is a perpetual sinusoid. Now question, what is a perpetual sinusoid? A perpetual sinusoid is a sinusoid that has been there for a very long time and that will be there for a very long time. What do I mean? I am talking about technically a signal which looks like this, a signal which is represented as by e to the power j omega t, right? So you can imagine this is a sinusoid. This is, of course, you know Euler's theorem, which says this is nothing but cos omega t plus j sine omega t. So again, we are dealing with a complex signal again, and again, anytime we want, we can take the real part of this and the imaginary part of this as well. We can deal with them separately if we wish. But the thing is, there is no ut anywhere to be found multiplied with this. If I multiply ut with this signal, then essentially I have a signal that starts at t equal to 0. Before t equal to 0, the value of the signal would be 0, right? So we don't have that. So this is what I'm calling a perpetually existing perpetual sinusoid, the sinusoid that has been there forever, okay, and that will be there forever. So if I take a sinusoid like this and excite the system, okay, and why are we exactly doing this? I'm going to explain that shortly, okay. So if I take that perpetual sinusoid e to the power j omega t and excite the system with this, so now of course my xt, which is the input, is e to the power j omega t, right? And with that said, if I take this and excite the system with this signal, so I'm writing here. So now imagine my input signal xt is this perpetual sinusoid e to the power j omega t. Of course, it's a sinusoid where the frequency of the oscillation is omega radian per second, right? Again, this is a complex representation. Complex representations often make the calculations simpler, right? So the output here under this scenario, the output is again going to be integration from minus infinity to infinity. I have g tau here, and now here I have xt minus tau, and this is the definition of xt, right? So xt minus tau would be e to the power j omega times t minus tau and d tau here. You see, this is simply can be simply derived from this, right? From this is derived very easily, right? So we are just replacing x t minus tau with the proper expression here, because this is the signal we have assumed. And why exactly I have assumed this kind of a signal, I'm going to explain that shortly. All right, so that's fine. Now let's expand this exponential here. So I have an integration that starts from minus infinity, goes up to plus infinity, where the variable is tau, and we have g tau. And really, I don't really know anything about g tau. The only thing I need to know about g tau is the fact that it is the impulse response of a system which is continuous time, linear time invariant in nature. That is exactly the thing that I need to know about this, nothing more, right now at least. All right, and here I have e to the power j omega t, and I have that multiplied with e to the power minus j omega tau, and I have d tau here, right? Now, of course, tau is the variable of this integration, so e to the power j omega t, this term can actually go outside this integration as a constant, because the integration will treat this as a constant, treat this entire term as a constant. So I can write this as e to the power j omega t, and this integration from negative infinity to positive infinity, g tau e to the power minus j omega tau d tau. But you might have already noticed that this entire expression, this entire thing here, whatever is here, okay, this entire thing, okay, let me just get the color correctly. Okay, hold on. All right, this entire thing that I have represented with blue, that's actually nothing but the Fourier transform of gt or g tau. Again, tau is a dummy variable here, it doesn't really matter. It could be x, it could be any other dummy variable really. But this is by definition the Fourier transform of gt, Fourier transform of the impulse response signal itself, right? So as the output, I can now write this as e to the power j omega t, and that's your j omega. So I am representing that j omega as the Fourier transform of gt, because that is by definition the Fourier transform of gt, right? Or g tau in this case, the same thing really speaking. So now notice carefully what we really got. Okay, let me just copy this here. Let me just copy this system here and definition here, and let's see that if this is the input to the system, then the output of the system would simply be this. Okay, so if this signal is the input to the system, if so you can see if this signal is the input to the system, then this is the output to the system, right? All right, what exactly happened really? See, as you can see, the input signal directly somehow appears here in the output as well. So let's just write it down. So we see, let's just write it down, write down what we just have seen. Okay, this is what we have seen. So this is what we have seen. If we excite a continuous time LTI system, again we are just dealing with continuous time systems, that is why we are imposing this continuous time criteria here, otherwise we wouldn't really. Okay, this is true also for discrete time LTI systems. Okay, as long as the system is LTI, this is true. This kind of definition will be true with slight modifications, okay, in the signals definition itself. In any case, if we excite a continuous time linear time invariant system, now there are certain conditions which I am assuming and I'm going to tell you shortly, but let me just write it down for the moment. So if I excite a continuous time linear time invariant system, now there is just one problem here, is that we blatantly wrote, we just directly wrote from here, from this definition, from this very expression, we just wrote Gj omega. But of course that's a Fourier transform, again we mentioned, but there are certain conditions, those conditions needs to be satisfied by this signal, then only the Fourier transform can even exist, right? In order for this Fourier transform to actually exist, which means in order for this integral to actually converge, there are certain conditions this signal must satisfy, and these conditions are known as the Dirichlet conditions, okay, named after Gustav Dirichlet. So you can see those conditions, and these conditions I can just make a small recap of that. These conditions are that this signal will have to be this signal should not have any what should I say, this there are three conditions again. Okay, the condition is that this signal should be bounded first of all, which means this signal cannot go to infinity at any point. Okay, throughout this signal span, this signal GT cannot go to infinity. Okay, so again this cannot become unbounded. Okay, that's the first thing. Okay, then this signal should have finite number of extremas in any given interval. Okay, so finite number of extremas. Okay, so this signal should have finite number of maximas and minimas, those are extremas, right, in any given span. And number three, this signal should have only finite number of finite discontinuities. Okay, finite number of, again, finite number of discontinuities. Okay, so this signal should satisfy actually these three conditions in order for the Fourier transform to actually exist. Okay, these are named after Gustav Dirichlet. You can just notice I said finite number of finite discontinuities, but I did not write that because I'm already saying that the signal has to be bounded. So that essentially makes the discontinuities bounded. So only jump discontinuities are allowed really. Okay, infinite discontinuities are not allowed. If these conditions are satisfied, then these are the sufficient conditions for a signal to have its Fourier transform expression. So this signal, so this integral will actually exist, and if and the sufficient conditions are these. Okay, all right, so we're assuming these conditions, and we are going to come back and see under what scenario these conditions are satisfied, but we are assuming these conditions. Okay, we're assuming that the impulse response of the system actually satisfies these conditions. All right, under that scenario, okay, if we excite a continuous time LTI system, let's just keep a small space here, okay, to put the Dirichlet conditions in a single word. That is what I'm going to do shortly. But the thing is, okay, if I excite a continuous time LTI system that satisfies certain conditions, so that the Dirichlet conditions are also satisfied by the impulse response. Okay, with a perpetual sinusoid, sinusoidal input rather, and the input is e to the power j omega t. Okay, then the output is also a sinusoid, that's also a perpetual sinusoid, sinusoid, and let's define this as e to the power. So we have seen that times the Fourier transform of the impulse response, right? Now, what do I mean by applying a perpetual sinusoid? How can I obtain a sinusoidal signal that has been there for a very long time and that will be there for a very long time, perpetually will be there? Okay, so this kind of definition is kind of vague, but at least for in our context, we can assume that this is a signal, okay, that has been applied on the system for sufficiently long time. Okay, so this signal, this input signal, if this input signal acts upon the system sufficiently long, okay, so that the system gets enough time to reach a steady state, okay, then we can assume the signal to be something like this. Okay, if this signal appears, so this is kind of a sinusoid that was applied to the system sufficiently long ago, such that right now at this very instance, you can understand the system has reached a steady state. So whatever output we are seeing here is the steady state output of the system. Okay, so that is a way of rephrasing what we just stated, right? So instead of calling this a perpetual sinusoid and this is the perpetual output that has been there for a very long time, you can imagine that this input signal was applied long ago, long enough. The time at which this was applied was sufficiently way back, so that this system got enough time to stabilize, or rather enough time to settle down. So this was essentially the steady state output. So instead of writing this, I'm going to say if we excite a continuous time system with just a sinusoid, I'm going to explain this as sinusoid, then the output is also a sinusoid in the steady state, right? I can say that because this technically means the same thing. And this kind of steady state has a special name. This is called a sinusoidal steady state. You can understand why, right? The input is a sinusoid and the output also has a sinusoid in it. So it's a sinusoidal steady state, right? So if I excite a continuous time LTI system with a sinusoidal input that looks like this, then the output is also a sinusoid that looks like this in the steady state. Now here is the condition. I have to impose certain condition so that GT has a Fourier transform. The Fourier transform actually converges for GT, right? And what is the condition? The conditions are these Dirichlet conditions. And now if you have gone through the lecture on stability, you already know that a system which is stable, BIBO stable to be exact, a continuous time linear time invariant system which is BIBO stable, okay, if the system is BIBO stable, then its impulse response also satisfies the Dirichlet conditions. So essentially, having a BIBO stable system makes sure that the impulse response of the system also has a Fourier transform representation, right? So the assumption is that we have a continuous time LTI system which is stable. So we're going to write, if we excite a stable continuous time linear time invariant system with a sinusoidal input like that, then the output is also a sinusoid that looks like this in the steady state, right? I don't think there should be any confusion with this understanding here, right? Now let's think about I just miswrote the output here. Let's just make this YT. All right, that's the output. Now of course this is the input and this is the output here, right? So, and again, this is nothing but a complex number really. For a certain frequency, this is just a complex number. If we have the transfer function, then this is just a complex number. And let's explain this G, omega term here, right? Now, if you go back to our lecture on Laplace transform, the very first lecture on Laplace transform, you would see that we defined Laplace transform of a signal. Okay, Laplace transform of a signal. Say I want to take the Laplace transform of, say, a certain signal xt maybe, right? Say we want to take the Laplace transform of, say, gt. Okay, we express that as gs, and if we take the Fourier transform of, say, gt, we express that as gj omega, really. But the thing is, we mentioned, or rather we proved, that Laplace transform was kind of an extension of Fourier transform. What Laplace essentially did, he took Joseph Fourier's research papers and modified that to accommodate more signals. Okay, so what he did, he essentially multiplied this signal. Okay, he essentially multiplied this signal with an exponentially decaying factor for the most part, for most cases. Okay, an exponential factor that would make sure that this signal actually has an absolute this signal absolutely integrates. Okay, the point being that if I take the Fourier transform of this signal, essentially we are calculating this integral. This might or might not converge depending on the signal, and very few signals really converge with this definition of Fourier transform. But if I multiply this signal with a real exponential that kind of looks like this, where sigma is the real number here, okay, positive or negative depending on the signal itself, then we can kind of ensure that many other signals that do not have a Fourier transform representations, because they were not integrable earlier, can now be integrated. Now if I take the Fourier transform here, I get this expression, right? And this is nothing but the definition of Laplace transform itself. Okay, and you can go back to that lecture that we had on the Laplace transform, the very first lecture on Laplace transform. This is the definition of Laplace transform. So we can say that rather this is kind of an identity that Laplace transform of a signal gt is nothing but the Fourier transform of the signal gt times a suitable factor here. And how do I make that suitable? I make sure that this signal, the multiplication of this ensures the convergence really of the Fourier transform. So that's pretty much the definition here, right? And you understand that while we define Laplace transform, this is essentially the Laplace. So this is essentially written as gs, and this is essentially written as gj omega. And when we do the expression integration, whatever, okay, what we really do, we have an integration here, right? So again, the Fourier transform expression of gt, let me use a different ink, I think. Okay, the Fourier transform of gt times e to the power minus j omega t, sorry, e to the power minus sigma t, that's essentially this. Okay, and now this becomes e to the power minus sigma plus j omega t and dt. Okay, and for Laplace transform we just define this sigma plus j omega as s. So really speaking, this s is nothing but sigma plus j omega, right? And as you can see, for the for this frequency response, for this idea that we are developing so far, we have the output where we have gj omega. So essentially what are we doing? We are if I have the transfer function of the system using the Laplace transform. So if someone has used Laplace transform, the differential equation of the definition, and created a transfer function with s in it, then we can replace sigma equal to with 0 and get the transfer function that is suitable for this. So this is again called the frequency response function, not known as the transfer function, but this gj omega is known as the frequency response function. I'm going to explain why that is called the frequency response function. But in any case, all you have to do in order to get this gj omega is just replace s with j omega, or very specifically, s is nothing but sigma plus j omega. We just have seen that, and we just write sigma equal to 0. This also has some better explanation in the fact that if I have a stable LTI system, in that case, if you calculate the output for any given input, you would see that this sigma term will appear on top of exponents. Okay, and for stable systems, this sigma will be negative. For stable systems, will be this sigma will be negative. Again, for better explanation, please go back to the lecture on Bibo stability. Okay, we have derived all these things. Okay, we will see that this sigma will appear on top of exponents, real exponents. Okay, and there will be other things multiplied with those parts, right? And if this sigma is, and for stability, all these sigma values should be negative. Okay, all these pole locations respectively will be negative. The real parts of the pole locations should be negative. So essentially I would have negative sigma values. Okay, so all those exponentials will become zero. All those exponential factors will become zero as time approaches infinity. So, and what does that mean? It means that if a stable system reaches steady state, then all the factors that had sigma in it will vanish. And as such, sigma vanishes if I give it enough time. Then again, that comes from the idea of steady state here. That is why we have this perpetual sinusoid here. All right. So with all that, we can see why we replace S with j omega. For the most part, that is it. All right. Again, you have seen this mathematically. You have seen this, and with other understanding of the subject, right? So this is the input to the system, and that is the output of the system, right? So now, really speaking, if I want to measure the magnitude of the input, if you want to compare the magnitude of the input and the output, what do I really see? I see that the magnitude of the output divided by the magnitude of the input, which I can write as this, is again, these are complex numbers, so I can again, if these were real numbers, I can just could have just written like this. So let's take the magnitude here. So again, we know that this is e to the power j omega t and then gj omega, where gj omega is the frequency response function, but I haven't defined frequency response yet. E to the power j omega t, and of course this has a mod of 1 really. Okay, the modulus of this complex exponential is 1. You can see why, because if you go back, you know the very definition of this. The very definition of this is e to the cos omega t plus j sin omega t. So the mod of that would be root over cos square omega t plus sin square omega t. So that's 1. So this is also 1. So this is mod g j omega. Okay, and why am I saying this? You'll see why. And when we calculate the difference between the phase angles of the output and the input, of course they are sinusoids, so they can be considered to be phasor quantities. So if I calculate the difference between the phase angle of the output and the input, so we are considering the input to be the reference phasor here. Okay, so we are calculating the phase angle of the output with respect to the input in a sense, right? So that would be the phase angle of the output signal, which is e to the power j omega t times gj omega, and minus phase angle of e to the power j omega t. And of course we know that the phase angle of product of two complex numbers is the sum of individual phase angles of those complex numbers. So of course this is a complex number here, and this is also a complex number. So that way I can see that this becomes the phase angle of e to the power j omega t plus phase angle of gj omega minus phase angle of e to the power j omega t. And of course these two will cancel out, right? And as such we have angle of gj omega, right? So what have we really seen? We have seen that the change in the output is also a sinusoid really. Okay, as you can see, if I bring this back here, okay, if I bring this back here, I can see that the output is really also a sinusoid, right? So if the input is a sinusoid, let me just write this more clearly here. Let me just write this more clearly. I have seen that if the input is a sinusoid represented like this, e to the power j omega t, then the output is also a sinusoid. Okay, and of course of the same frequency. That is why we have e to the power j omega t there. Okay, e to the power j omega t, and of course that's multiplied with gj omega. Now this actually indicates that this is a complex number gj omega, and the magnitude of this complex number will actually get multiplied with this and change the magnitude of this, right? So the magnitude of the output is nothing but the magnitude of the input times. So if I take the magnitude of the input signal and multiply that with this magnitude of this gj omega function, I get the magnitude of the output, right? So I can do that, right? So I can write that this is just like that. So this is the magnitude of the output. And also, what is the phase angle of the output? The phase angle of the output can be determined by taking the phase angle of this complex number gj omega and adding the phase angle of the original input signal, right? So whatever phase angle the original input signal had, we are assuming it to be the reference phasor. So we are assuming that phase angle to be 0, which I can do. Okay, so we have to just add the phase angle g j omega here, right? Whatever phase angle it has. Now this thing, so what I have right now can now be again simplified for real sinusoids, right? So if the input is something like sine omega t, okay, then the output is going to be mod, say if the input is something like a sine omega t, the output is going to be something like, say, b sine omega t, and say plus a phase angle. Okay, it could be a negative, positive, whatever. So we are assuming this signal to be having a 0 phase angle, because we are assuming that to be the reference phasor. All right. So with that understanding, we now know that this ratio of the magnitudes of the output to that of the input is entirely determined by the magnitude of this complex function here. Okay, and the phase difference between the output sinusoid and the input sinusoid is entirely determined by the phase of this complex function here, right? And this complex function gj omega determines how the magnitude will change, or how this system, okay, this is the system, right? How this system will change the magnitude of the input signal, okay, or rather change the magnitude of the input signal. And this angle phi, angle of gj omega, determines how much phase shift will there be in the output signal compared to the input signal. Now this function itself is a frequency dependent function, so this is entirely dependent on frequency, right? So if the frequency changes, the value of mod gj omega and the value of angle gj omega will change. And by virtue of that, if I apply a sinusoid of the same magnitude, same phase angle, but a different frequency, but if I change the frequency different, make the frequency different, then what happens? The system will probably behave differently, because for a different frequency, the value of mod gj omega and the value of angle gj omega will be different, because that's the function dependent on the independent variable omega itself. So in that sense, if I apply sinusoids of different frequencies to this LTI system, the outputs, the magnitude of the output will be determined by the modulus, by the magnitude of this complex function here, and the phase angle will be determined by the phase angle of the complex number here, right? So this is called the magnitude response, and this is called the phase response, right? So, and together they are called the frequency response of a system, right? How the system responds to different frequencies. Okay, and how did we think about that? We thought about the different frequencies by exciting the system with a perpetual sinusoid, or rather we excited the system with a sinusoid and allowed enough time for the system to reach its so-called sinusoidal steady state. So that's now the time has come to define frequency response, right? So the thing is, if we excite a stable continuous time LTI system, again I'm repeating the fact that this does not have to be continuous time. This only needs to be linear and time invariant. Okay, but again we are talking about continuous time systems throughout the course, so we are assuming continuous time here. Okay, so if I excite a stable continuous time LTI system, really I should put this in brackets. Okay, continuous time LTI system with a sinusoid of a certain frequency, then the output in the steady state again, if you think like an engineer, you can see if I don't say a stable system, then I don't really have something called a steady state, right? I can't even reach a steady state if I don't have a stable system, right? So if I excite a stable continuous time linear time invariant system with a sinusoid of a certain frequency, then the output in the steady state will also be a sinusoid of the same frequency the magnitude, the ratio of the magnitude of the output to that of the input equals input rather is determined by mod gj omega. Again, we define gj omega as the Fourier transform of the impulse response of the system, right? So far gj omega is the Fourier transform of the impulse response of the system. Okay, so the ratio of the magnitude of the output to that of the input is determined by gj omega, and the difference between the phase angle of the output and the input. So phase angle of output minus phase angle of input, and input is determined by, instead of determined I could say just exactly equal to, determined by the angle of this. Okay, these values change based on, rather depending upon, the frequency omega of the applied signal, of course, and as such mod gj omega is called the magnitude response and angle gj omega is called the phase response of the system. And together they are known as the frequency response of the system. So that'll be it for this video, and in the next one we are going to see how we can actually calculate the frequency response for realistic systems, and then we are going to do frequency response plots, specifically the Bode plots here. So thank you very much.